Good day everyone. Today, we present our research entitled, Experimental Evaluation of the Flexural Strength and Crack Behavior of Foam Concrete Beams with Varying Density Levels. This study focuses on how foam concrete behaves under bending loads, particularly in terms of flexural strength and crack development, using different density levels. It also examines how the internal pore structure of the material influences its structural performance under stress. Before we proceed with the discussion of our methodology and results, we would like to introduce the people behind this research. Here are the members of our research team. We would also like to express our sincere appreciation to our research advisor for the guidance, technical insights, and continuous support throughout the development of this study. We will now proceed with the step-by-step experimental procedure. The process begins with the preparation of the beam molds. We used wooden molds with dimensions of 4 inches by 4 inches by 14 inches, which served as the standard size for all test specimens. For the foaming agent, we used sodium lauryl sulfate or SLS, a commercially available material sourced through an online shopping application, specifically Shopee, making it both accessible and practical for laboratory use. Once the materials were prepared, we proceeded with the dry mixing stage. Cement and sand were thoroughly blended to ensure uniform consistency before the introduction of foam. Next is the preparation of the foam. The SLS solution was mixed with water and then aerated using a hand drill fitted with a mixing adapter. This process produced stable foam with consistent bubble formation, which is essential for achieving the target density levels of the foam concrete. After foam generation, it was carefully combined with the dry mix using a folding and blending technique to prevent collapse of the air void structure. Proper handling at this stage is critical, as excessive mixing can significantly affect the material's final density and strength. Once the mixture reached the desired consistency, it was placed into the prepared wooden molds. During casting, the mixture was carefully poured and subjected to tamping and light hammering to reduce large voids while preserving foam stability. The specimens were then left inside the molds for 24 hours to allow initial setting before demolding. After demolding, the samples were cured for 7 days, 15 days, and 29 days, allowing sufficient time for strength development. After curing, the specimens were tested using a universal testing machine, UTM, to determine their flexural strength. During testing, we observed both the maximum load capacity and the crack initiation and propagation patterns, which provided valuable insight into how density affects failure behavior in foam concrete beams. Based on the results, a clear relationship between density and structural performance was observed. Across all curing ages, flexural strength consistently increased from 7 to 29 days, confirming the importance of proper curing in improving internal bonding and overall strength development. Higher density foam concrete beams consistently exhibited better flexural performance compared to lower density specimens due to reduced air void content and improved stress distribution. Meanwhile, conventional concrete still achieved the highest flexural strength among all samples, serving as the benchmark due to its dense and continuous matrix. The results also showed that the SLS foaming system effectively produced stable foam, resulting in relatively uniform pore distribution and consistent behavior during testing. While foamed concrete showed lower strength compared to conventional concrete, the higher density mix demonstrated promising performance, indicating its potential use in applications where weight reduction is prioritized over maximum strength. Overall, the study confirms that foam concrete performance is strongly influenced by both density and curing age, and that proper control of materials and mixing procedures is essential in achieving reliable structural behavior. In conclusion, the use of sodium lauryl sulfate as a foaming agent, combined with controlled mixing, proper casting, and adequate curing, plays a crucial role in the flexural performance of foam concrete beams. Although foamed concrete does not surpass conventional concrete in strength, it offers a viable lightweight alternative when properly engineered, particularly at higher density levels. Thank you for watching.